Okay, everyone, so a few announcements. First off, I have to show you really quick the best part of my classroom. I couldn't bring it to school. This is my favorite part of the classroom. If you don't know Harry Potter, you're not probably going to understand. I made my child a baby mandrake for him. I wanted to bring him and just like sit him on the desk as a little plant, but you know. So, okay, second thing. Here's my wizard trick for the day. Can't dress up as a wizard and not do magic, right? Actually, we have lots of magic tricks today, but this one's just for fun because it doesn't really fit into the lesson. Guardian Leviosa. Oh, that was weak. See the other ones? Throw them
What? Wait, what? I'm quite disappointed with that. Why did that not fly? What kind
I
of...
must have not done the right swish and flick.
Yes.
Oh, yeah, he said
What kind of picture is this?
It's actually what, if anybody sews anywhere, it's like what patterns are made out of.
What is going on? This is making me so
Good as it
sad.
did. Running out of my magic, I guess. Okay, third time's a charm. Just keep doing this all day.
You often teach us on that. Does the temperature, like the air or something, have to do with it? Like colder air?
Could. It's cooled down since the other period. Or if it's too warm. I feel. That's as good as I got. Maybe a vent's on somewhere. Maybe there's a current blowing.
Moving, like, yeah, blowing it down.
Well, kind of cool. Normally it floats all the way to the ceiling, but we'll try at the end of class today. See if it works. Okay, few announcements. Number one, just a reminder, you need to get your AP test paid for, reserved, $95 for the financial office on my school fees. Okay, once again, you can get refunded the $95 if you decide not to take it, but it's cheapest to pay now. If you decide later, it's going to be more expensive. Okay, second thing, majority of you did this, but there's a few who have not taken the Unit 2 test, which you were supposed to do on Wednesday at home. If you are one of the 3 people who forgot, please get it done by tomorrow at 9 p.m. so I can unlock so people can see what they did wrong, what they did right, and we can start on test corrections. So tomorrow I will open it up. If you don't take it by then you'll be taking a different version than everybody else. Because I want to get the scores out to those who did take it. And next week I'll talk more about that once everyone has taken it. So, okay. Also, just a few things on Canvas. I messed up and the upload links for 2.1a, 2.1b, and 2.5 were there, but I didn't have due dates assigned to them on Wednesday, which, if they don't have a due date assigned, they don't pop up in your, like, to-do list. So I think a lot of you didn't see them. So I've left those open through the weekend, so if you didn't, or if you, like Landon, uploaded all of them to 2.7, a few other people did that as well, just get on and if you could upload them separately for me, just because it'll make grading easier. So, but those are open as well. There's also a link to upload your book notes if you didn't see that, and that stays open till tomorrow as well. So.
There's only 2 book notes, right? Like 2.
Yeah, just 2 pages is all you should have. Yep, we only had 2 readings last unit. So, okay, so there's that. Today what we're going to do is we're going to be talking pretty much more about intermolecular forces, with the big component of connecting it to what we see happening. And explaining something. So I'm going to be doing various demonstrations during our lesson today with the objective of you try to come up with an explanation of what's happening at the molecular level. All of them kind of going back to this theme of intermolecular forces. Also side note, the Vesper Lab is also due today. I think it's closing at 9 p.m. tonight if you haven't turned that in yet. So make sure you get that turned in, okay? Okay, I'm going to make a little flow chart just to connect what we learned last time. You're welcome to write this down somewhere else that's not like directly in your notes. But if not, then just kind of follow along. So what we want to look at here is how to identify the intermolecular forces in a substance. First off, can someone by raise a hand remind us what is an intermolecular force in general?
It's a force in between molecules.
Good, Taylor, that's nice this time. You said it's simple, but just perfect. It's a force between.
Oh, can I get my smiley face dressed?
Okay, so it's a force between two different atoms, two different molecules that they experience. Okay? So if I'm given a formula, and we need to identify the intermolecular forces inside that substance, the first thing you need to know or identify is that substance ionic, covalent, or metallic? Okay, so that's the first question you ask yourself. Did you say, okay, is it ionic? Is it covalent? Or is it metallic? Okay, I'm going to use NH3 as an example as we talk about these things. So, how do I know from a formula whether something is ionic, covalent, or metallic? Max?
What the elements are that are bonded in the compound.
Yeah, good. So we look at the individual elements. Ionics are what type of elements?
Metal.
Good. So metal and the non-metal, or combination of them. Covalent is just non-metals, and metallic is just metals. Okay, so first thing you look at what type of things are present to know what type of bond it has. Okay, how's my face for that, Max? Okay, now, so this right here would be covalent. The next step is, if you identify it's covalent, the next question you ask is, or you identify is it a molecular covalent? Or is it a network covalent? Okay, so we identify what type of covalent it is. Is it a network covalent or a molecular covalent? Does anyone remember from last time what goes on at the molecular level for a network covalent? What's going on there, Evan?
Isn't like everything bonded to everything is like really strong?
Pretty much. You have tons of bonds all over the place, shared in all directions, lots and lots of bonding, and typically it makes them very, very strong substances. How's my face for that, Evan? So here's what you need to know about networks from what I gave with the AP test. There are 4 things I would just kind of memorize and know, like, hey, these form networks. Outside of these 4, if a question were about something different, they'll show you a picture of one. And from the picture, you should be able to say, oh yeah, that's a network of bonds, because the picture will show that. Okay, so number 1, we talk about diamond. Forms a network. Graphite also forms a network. Now, what element are diamond and graphite made of?
Carbon.
Just carbon. Alright, so this is pure carbon, this is pure carbon, just different structures. Okay, another one that does a network is silicon dioxide, SiO2. Save on my roll really quick. which by the way, this is glass. So glass is a covalent network. And then pure silicon, so when silicon bonds with itself, it's also a covalent network. Outside of those four, there are others, but once again, they would give you information for you to know that. It is kind of significant to notice though, find carbon and silicon on the periodic table, everybody, and look at their relationship to each other. Right, so they're in the same family. Why, any thoughts of why that family would be good at forming networks? Zach?
They have like a half bond, or like half like the, like their shells are half full.
Yeah, so they have 4 electrons, right? Meaning they want 4 more. So often they bond 4 times each, which is where you get all the bonding of your diamonds and graphite is because of, that's where we get like carbon can do cool like pentagons and hexagons and different things like that because of all the different bonding. There's another really cool structure of carbon they discovered just a few years, I guess it's been a while, but fairly new in time, as a compound known as a buckyball is its nickname. Has anyone heard of these before? No one? So at the, I'll see if I can find a picture to show you, but at the molecular level, what it is it's literally, it looks like a soccer ball, but that's how the molecules shape. Is you literally have carbons, and they form this cool little sphere. But anyways, Carter, did you have your hand up?
Oh, I did. I also was noticing that carbon and silicon don't have, I don't think they, wait, do they have a charge?
Nope, they don't. They don't typically form ionic bonds. You're right
Yeah.
there. Yep.
And so they're not like as specific, like you don't form ionic bonds, but they're not like specific.
Yes, no, great observation as well. Yeah, because they don't ever give up those electrons. They're always doing that shared relationship. Yeah, that's why like the bottom ones, right? Like these ones don't form networks because they do form charges. So yeah, good observation. Okay, questions on networks? Okay, so pretty much if it's not one of those 4, you're gonna assume it's a molecular covalent. Now, once I know it's molecular covalent, we then have 3 intermolecular forces it can have. And keep in mind it can have 1, it can have 2, or it can have all 3. So the first type of intermolecular force is we have dispersion forces. We then have dipole-dipole forces. And then we have hydrogen bonding. Okay, can someone help us remember what happens? Let's do this first. How do I know if something experiences dispersion forces?
Everything does.
Everything does. The answer is just yes, right? Everything that is a molecular covalent has dispersion forces. What goes on at the molecular level in a dispersion force? Like what's going on there, Carly?
It like has momentary positive and negative like charges. Like
Good. And what causes that momentary distribution?
So because they're sharing, the electrons can move around more.
Good.
So at any given moment, there could be more or less electrons on either side.
Yeah, so it's just because electrons are not stagnant, right? They're always moving, and so they can happen to move to this side and make it a little more negative, and then thus the other side a little bit more positive, and there's your magnet. Keep in mind that all forces are all about positive and negative things. Some are just a lot stronger positive and negative than others. In this case, the dispersion is very weak, because it's just that temporary shift. But that's why everything has it, is because everything has electrons. Have a smiley face for that, Carly. So we know that NH3 has dispersion forces. Yeah, Evan.
This is kind of a little off topic, but so if an atom was at what's it called? Ultimate zero or something?
Oh, at absolute zero?
Yeah,
Uh-huh.
absolute zero, my bad. If it was at that, would all the electrons stop moving too? So would it
Ooh.
make like a dispersion? But like a little.
Don't know.
That's really deep and philosophical.
That is very deep. From my understanding of the definition of absolute zero, the definition is that's just the point at which the molecule stops moving.
Okay.
But I don't think it's referring to, I don't know what happens to an atom if its electrons were to stop moving. Because like, well that's weird, that's hurting my brain. Because like literally like, one of the weirdest things, right, is that atoms are like mostly empty space.
Mm-hmm.
They don't feel empty because of the electrostatic fields of the electrons.
Yeah, so if the electrons stopped, it would just be like a few electrons surrounding like
Yeah, you could like, I mean, yeah, like if I could
You could walk
theoretically
through stuff.
stop the electrons in this wall, I could like walk through the wall.
Well, and the wall would probably collapse.
Vaporized.
Yeah, I don't know, but that's the thing is I don't know what else would happen, you know what I mean?
Yeah.
I don't know, that's weird.
It's just
Good question. Okay, dipole, dipole. How do I know if something has this force? What do I look for? Math?
If the molecule is polar,
Good. Okay, so the question is it polar or not? If it's polar, then yes, it has dipole forces. If it's not polar, then it doesn't have dipole forces. So, given a formula, how do I identify if something is polar or not? That's what I have to do.
Like, if the charges bounce out, so like, yeah, the charges bounce out in the molecular geometry.
Good, so we have to look at its structure and see, are all the electrons going one way? Or do they actually cancel each other out? So you've got to take it into 3D space. So this in 3D is a trigonal pyramidal. So that's where you have one in the center and then you have a little, well, no, that's not pen. Is this still on the camera? Did I put my
Yes.
Yeah,
okay,
you're
thank you. This, by the way, is how chemists draw in 3D. They draw wedge bonds to say, hey, this one's popping out at you. And then they draw these dashed ones to say, hey, this one's going backwards. So it's pretty much kind of showing this. If you squint your eyes, you can see it pop out. Okay, and then the reason why is it doing this is because there's a ghost on top. So like Zach was saying, we have to see where's the electrons going and are they canceling out. In this case, all the electrons are being pulled this way. And because of its shape, do they cancel out?
No.
No. So this is polar because this side of the molecule would be more positive, and this side of the molecule would be more negative. That's the dipole. Di meaning two, pole of positive and negative. Okay? So that's how I know something is polar. Okay? How do I know something experiences hydrogen bonding or not? What are we looking for there? Taylor?
Doesn't it have to be like oxygen, sulfur, or oxygen, fluorine, nitrogen, and one more?
Nope. So just
Oh,
those
just
three. So
those
it's
three.
hydrogen with NO or F. One of those three. Now keep in mind, it has to be directly connected to those ones. They both just can't be there, but they have to have a bond between them. So for ammonia, the H is connected to an N, so it does have hydrogen bonding. The difference between hydrogen bond and dipole is that because it's so electronegative, and we literally have just left a bare hydrogen with no electrons, it's just really that it now makes this extra positive and that extra negative. So that's why it just becomes a little bit stronger of a force. So, questions on our three forces so far? These two are straightforward. If something is ionic, it has ionic bonding. If something is metallic, then it has metallic bonding. There's not differentiations within those types of bonds. Okay, so open up your notes to that table we left off last time. This one. let's do this and then I'll decide where to go from here. So based off that flow chart we just did and what we discussed, take your thumb for me and use it as like a ring, okay, like this. So thumbs up means I feel like I could do this table all by myself and do a good job. Thumbs down is I can't do it at all, and then you can go somewhere in the middle. How you feel? And this is just for me to kind of see. Okay, that's not a bad place to be. So let's do this. I'll give you 3 minutes to work on this with your table buddy for some smiley faces to fill in what we didn't get last time. Okay, and then we'll check it in a second. Ready, set, go.
So I was going by last time. These are the
So, it's hydrogen. Gold and water metal. So it's going to have
and they do have dipole attraction because it has.
Oh wait, no.
Because it has. It's not.
F2 just had a blend.
Wait.
No, it is.
This? Oh yeah, it's so much harder. So.
Wait, no.
Typically we just let it pass now it is the
In this bottom.
can't experience this other with graphite. The graphite sheet itself is a network, but it's stacking up the sheets.
That's why
I classify as a network only just safe network. You are right within that network, it could experience between those different
It's
Oh,
kind of like, I guess, technically like a diamond to another diamond. Could have dispersion forces with each other. That's why they don't really stick because they're so strong.
it's covalent, but
This is
it's definitely polar.
It would double bond.
Wait.
No, it's not.
Yeah, because they cancel each other out.
So it's not polar, so it's gonna have bond forces, but not.
That's that's it.
Just like
Okay. Just one. It's gold.
no.
It's gold under copper.
Alright, you got 30 more seconds.
SiO2 is glass. I don't know. Silicon is not. It's glass, so.
It's
But
just,
I'm
it's
not
just from, darker, remember?
Okay, wait, what about
Gold is metal. So it's just metallic.
but it's just by itself. So would it be a bond?
Well, it's she said earlier, it's if it bonds, like when she just says AG, she means that it's AG.
Oh.
That's what she said earlier.
In 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, so for every substance you identify correctly, you can have a smiley face for it.
Oh,
Last time we did the first 2, was that all?
And
And the ionic one? Okay, so for HCl, you should have identified yes, yes, and no for the miss.
Wait, so it's a point for every check mark you get, right, or each
For
element?
Check mark. I will check.
check.
Yeah.
Good question.
Actually, we only get one more check mark.
Yeah.
Oh, really?
Yeah.
I guess the first one would have been the best one, huh? Maybe I'll throw it.
We didn't do that one class.
Okay, this one you should have identified dispersion. That's it, nothing else. This one is the network. And silver is metallic. Questions on identifying intermolecular forces. That's what your homework 3.3 through Canvas is doing. Is I've given you like 40 different substances and you have to sort them by their intermolecular forces. Okay? I did it through Canvas because I wanted you to get immediate feedback of right and wrong. But you can take it, I think, up to 5 times. So if you get it wrong, you can try it. Okay, here's what we're going to do for our little activity. Pull on a piece of paper. Just a lined piece of paper. You can probably split it in half with a friend. Use front and back. Okay, so what we're going to do here is I'm going to show you a variety of magic tricks.
I love magic tricks.
Magic is just science that can't be explained.
And your job is to try to come up with an explanation for the magic. Okay? Now, in terms of, this is going to go into your grade as some lab points. But you're not grading in terms of if you're right. All I ask is that you try. So as long as you come up with some reason, even if it's wrong, you'll still get credit for participating. All we're trying to do is just activate that chemistry brain, right? Be thinking on the molecular level, like a chemist, so on and so forth, okay? You can discuss with your neighbors to share ideas as well with your explanations, okay? I don't know, I think we have what, 1, 2, 3, 4, I think I'm having 6 total, so just so you know, like, I think there's 6. Okay, so first one, I'm going to bring these funny looking things around. Don't touch it until I tell you to. I'm just going to kind of spread them out so people can see, and then you can take turns holding it. Okay, so don't touch it yet.
So wait, we can use our whole table for this one?
Yeah, yeah.
Which graph?
Okay, I'm going to put, you guys kind of share with them and look at that one. And then I'll give one to your row. And then Isaac and Lem, you kind of look down here, and then you guys can pass it amongst yourselves. Sure. Okay, so don't touch it.
So magical.
Okay, here's what I'm going to do. Somebody, and once again, everyone can try it after the first person, but to start it. Okay, you're just going to pick it up from the top, and then wrap your hand around the bottom and observe what happens. Go ahead. You're not going to get shocked, by the way. Last period, someone was like really nervous, like, what's it going to do to me?
I don't like this.
Make it to the top, come on.
Yes.
Is this one of these self-moving liquids that don't have
Okay.
friction?
I'm not going to tell you right now. You tell me. Okay, so you can pass around, let other people fill it if they want. But what you're writing on your paper is explain to me. I guess. This wasn't tipped over the entire time, was it? Okay, can I borrow yours for a second to show the camera?
Oh! Hey, can we see?
Okay, is this on the camera, Lynn? Isaac? Okay, so here's what you're explaining at home, students.
Wait, why? Why?
Like in terms of pressure, like it would make like heat it up.
Well, it must be like.
Wait.
Because like heating warms up just a little bit.
What are we gonna say? Well, it's not.
Like what type of bronze ads?
You're just explaining how this works, like what's happening at the molecular level that's causing this to happen.
Well,
I think the
So all answers should be based on the molecular level idea. Now they're all going to link back to intermolecular forces, but your answer should just be based on the molecular level explanation, okay?
Oh, maybe because there was something else.
The confusing part is if it was had like a really,
What's
really
gonna
low
happen? Something
you know,
to heat.
how does all the liquid gas or whatever go to pipe it up? This is the
I feel like it
weirdest
would just
thing.
like build like pressure, and so maybe that.
What? And we're actually going the wrong way. Yes, exactly. And it's
Only one way to test it out. Put it on this part.
Wait, so it's
exactly. And then
Wow.
oh, that would hurt so.
This is how nerdy I am. This is what I got for Christmas last year. When I asked for it, and my husband was like, "What do you want?" They're so cool.
So if you touch the top, not the bottom, it's back.
like imagine like low
I don't know. I feel like it's a
Okay, you got 1 minute to write down your answer.
Oh,
Write down your answer once again. I don't care if you're right or wrong. It just has to be at the molecular view.
But it doesn't make sense. Yeah, it doesn't actually make sense.
It's wrong, I know it's wrong.
Well, you don't put down
I
wrong
know
answers.
it's right. We don't know it's right.
Well, that's true.
Well,
can we see that when you guys are done?
yeah. I know it's.
Okay. Anyone willing to share their hypothesis on this? Yeah, let's hear it.
So we think that the heat of our hand is heating up the air molecules to make them move faster, and then it pushes the water up really quick.
How many had something to do with heat of the hand cause the movement of the molecules? That is totally true, right? Yeah, that the heat of your hand is heating up the liquid,
It's heating up the liquid.
and in a sense, you're causing it to boil.
Whoa.
These are literally called, they're called hand boilers, is what they're called, little toys. Now, what's significant and why I relate this back, what does this tell us about the intermolecular forces of this liquid?
It's
It's very weak.
Very, very weak, right? How do I know they're weak?
Boiling so easily.
Yeah, right? If I tried to make this with water, would this work? No, you could hold it all day long and nothing would ever change, right? So the liquid inside of here is extremely low boiling point because it has very, very weak intermolecular forces. There's also a little bit, as we get into talking about vapor pressure and things, there's some pressure components in here as well that help it move, but the basic idea is actually just you're heating up a substance that has a very low boiling point, and so you're causing it to start to try to vaporize. It doesn't have anywhere to vaporize to, right? So that's why it just kind of goes back and forth. So very good. Okay, magic trick number 2.
That was actually nice.
Yeah, we start
Okay, this one's a little harder to see. Maybe if I bring it around.
So if you boil it for long enough.
So what I want you to explain here is the levels of the liquid in the tubes.
Like the little ones?
Yeah, so this one, the water's gone all the way to the top. And then it goes down in like a staircase formation. So pretty much what I want you to explain is how is the water all the way to the top here, but not in that first one. You can kind of see it. I'm trying to color the water so you can see it a little bit better.
And these all have to do with like intramural pressure.
Baby, oh yeah.
So it's not like water pressure.
Wait, is it all the same liquid?
Yeah, so all
Yes,
these water-
so it's all connected through the bottom. So I just poured it into this and then they filled up.
So it is water?
Yeah.
Or is it? So it's all water?
It's water, yep. Yeah, all water. I just dyed it green to try to help you see it better. So why is this tube higher than that tube?
There's something that's got
It's fine.
I was trying to decide if a different color would have worked better. Try for at home students. Can you see that? Okay, write down your guess. Once again, to get your points, you just have to have something for each one I show you.
Okay, so let's see.
Come up with something. You can't leave it blank.
It's gotta be something fresher.
Oh yeah, that one is bad. I'll bring it around to you.
Is it water?
It's just water, yeah.
Wait, it's all water?
It's all water.
Polar, and polar things tend to do random stuff that we can explain.
Wait. Is there something inside the tube? That is sweet. I don't know.
So this one is all the way to the tippy top. This one goes to there.
Why did Jesus
Huh?
It's even tilted like this.
Oh my
Oh, I
god.
thought it was backwards.
Okay, you got 30 seconds.
What are we even gonna
As long as your answer is based on the molecular view, you'll get your points, even if it's not quite right.
So if I just wrote magic.
Not sure how well that will apply
Okay,
in the
that's what
AP
you
test at the end of the year. You just get stuck, you're just like, it's just magic.
hydrogen bonds stick together on uneven wood? Let's go.
Okay. Anyone willing to share their thoughts on their reasoning? Whether it's right or wrong? Carly, what do you think?
I think this is probably really wrong, but I just kind of thought about like since water is really connected to itself, like the one in the last tube has the most like pressure from the other like water molecules because it's all like switching. That way, Yeah, and then it slowly had less and less pressure because there's less water connected to it.
Gotcha. Not a bad thought, and it does have a big component to do with the fact of how water links to itself through hydrogen bonding, right? The one thing you can't quite see, and hence why it's a magic trick, I'm going to bring it around and you can look at it from the top. You know, don't be angry when you find
Is there
what's
something?
going on with my tricks.
Well, it's
See the
just like
difference?
up four.
Is they just saying
There's just
plastic
gonna be a
lid
lid.
at the top?
Yeah, watch as there's a plastic piece
There's
at
a-
the top.
There's a lid.
You see the difference?
Oh my gosh, it's
Oh.
the air.
Can anyone tell what's going on?
There's a bigger hole as you go left, so more air is coming in, which is.
So there's holes at the top,
Oh, okay.
and they're
got
not
it.
equal in size.
I just.
So the air is Wait,
That's like weird.
I understand now.
So this one has the biggest hole. Now keep in mind, it's not that the air is pushing harder on this one than this one. Air pushes all the same.
Oh.
But the smaller the straw, the more easily the water can cling to itself and the walls and climb up the tube. This is literally how plants get their water from the ground. This is how roots work.
So the tube's on the same size?
The whole,
No, the
inside of the
tubes.
tube is small.
The whole, yeah, so this one is bigger straw than this one.
Oh. I thought it was just a bigger hole.
And it just like
I just thought, like, I
reflects
thought
off
it was
the
a
thing.
top part.
Oh, no, so yeah, the entire tube, this one is bigger than that one.
Oh.
It's a trick because they made it look like
Yeah.
almost all the same,
Oh,
Same.
it's like it's-
right?
But
But this is the idea of
these-
capillary action. Right, this is how capillaries work, is the smaller it is, those intermolecular forces can grab on and climb up higher. The bigger it is, right, like this one, right, in that case, this is where now the pressure is overcoming the intermolecular forces, right? So the bigger it is, the less they can climb up. So, questions on that? Yeah, Taylor.
If you were in our position and didn't know what that was, would you have been able to answer it?
How can I answer that question? Because I'm not.
Like
It's like asking me to forget what I know.
And someone showed you that magic trick, and you hadn't seen it before. Would you actually know, or is like the entire understanding of it in the fact that each tube is bigger? Or could you figure that out without actually knowing that the tubes were bigger?
No.
Okay.
Because that's the reason behind it,
So like it
right?
was literally impossible for us to know,
Well, it's kind of that thing of,
unless we like super guess.
here's how I think about it. This is how you kind of think moving forward, right? You have to come up with a reason for what you're seeing, right? And so even without knowing that it's different size tubes, seeing that this one is different from that one, there must be something different going on
Yeah.
in this tube than in that tube, right? So that's kind of where, like, as I show you the other tricks, kind of thing in that one's like, okay, there's something going on, maybe I can't see, right? That's causing it to happen. But did I answer your question?
Yes.
Okay. Okay, next one. I'm gonna bring, now you don't have to feel this if you are nervous. I promise it's not gonna hurt you. But if you wanna hold out your wrist, I'm gonna come and squirt you with a chemical.
Like wrist falls off.
Burn time is a
If you don't wanna do it though, you don't have to, and someone next to you can
Get
tell
to
you
be
what they
extra
feel.
Halloween.
But what I want you to explain is what you feel. Sound good?
Is this like some opioid?
And if you don't want me to squirt you, I won't. But I promise it won't hurt you. Just don't lick your hand.
Don't lick your hands.
But dude, that's what I do all the time.
Yeah, it's just something.
Okay, so observe how it feels, and that's what we're trying to explain.
Oh, it's so cold.
Hey, that's chilly.
Oh, it's like.
Yeah, my hands just dry.
Yo, look
Oh,
at
it is so
yeah.
cold.
Holy crap.
If you took a bath
Oh,
in
it's
this
so
stuff, would it
cold.
kill you?
Why am I so tempted to lick my hand?
Yeah.
Don't lick your hand.
Saying that made it a lot.
Now my hand's all dry.
Sorry, students at home, I can't squirt your hands. Someone explain to the students at home.
It's cold.
It was like
It's
cold.
cold. And now it's dry.
I have like
And then it's gone.
I have
Okay,
like
now-
a white scaly stripe.
You need to know that this bottle has been sitting in this room the entire day. It was not in the fridge. I have not chilled this liquid in any form. If I put a thermometer in here, it would read whatever the room's at, so it would read about 70 degrees.
What?
Okay, do I get a thermometer? No, I won't work, right? I say that all the time when people tell me facts. I'm like, okay, I'm a scientist. I don't believe everything Google says. You gotta prove it to me. Yeah, then I grab a thermometer.
Bro,
Alright, we have
so
another
like,
piece of
My skateboard is
alright,
cold.
what is it?
Probably strips away
It's not even a thing. Literally. She dropped it on my, she dropped a giant drop on my and she's gone.
Okay, so come up with a reason of why it felt cold when in reality it's not cold. So it's at 24 degrees Celsius. Sorry, this thermometer doesn't do Fahrenheit. But that's like room temperature. Questions, Zach?
That's pretty neat. Oh no, I thought, well, you were asking.
Oh, you have a reason. Okay, sorry, I'm just giving people 1 second to finish writing and then you can check.
Are we trying to figure out why it disappeared or why it's cold?
Both. Why did it disappear and why does it feel cold? Taylor, how's your paper look?
It's like there's a splotch on it.
Is it wet though?
No.
So I squirted his paper
Yeah.
and it's no longer wet.
Yeah, it's gotta be.
Here it is again. So I just squirted this paper. Looks wet. Less wet.
Oh. What? It just started disappearing.
fading away.
Okay? And then just to show the difference, here's water. Still wet. What's that? Yes. Okay, write your explanation.
Okay, is it, wait, you telling me it's a chemical we used really?
No.
I had no idea.
So that's why it felt cold.
Water, you know.
It's gotta be so cold, because it's like, that's why it feels so cold.
Yeah, like.
It evaporates so fast.
There's something written on the wall.
And then also, maybe that's also why it also made our hands dry because you have to
Stripped away.
Does anyone know what that is? Okay, Zach, let's hear it.
So I was
How's that
thinking-
working?
I was thinking the liquid is like, so the reason why it evaporates is because the bonds are weak, so it has a really low boiling point.
Good. Okay, pause for a second there just to reemphasize that. Huge takeaway. When something evaporates quickly, it has very weak forces. Right? There's not much holding together, so it doesn't take much for it to go away. Okay, carry on.
Also, it's like, it's probably very conductive, so like, it takes away the heat from your hand really fast, and that's why it feels cold.
Close. There is a transfer of heat, and that's why it feels cold. It's not so much that it's conductive, but it's how evaporation works.
So to evaporate, it has to use energy, so it steals the energy from your hand, making it evaporate in the energy.
So it's kind of, in a sense, like conducting. But that's literally why, like, when you get out of a swimming pool or out of the shower and you're wet, why you feel cold is because the water that's evaporating off your skin is sucking all the heat off of you. And so you feel cold when you're wet because it's the water sucking away your heat. Now this just does it so quickly, that's why it feels really, really cold. It's acetone is what it is. Some people might have noticed it by the smell. It's the same thing that's in fingernail polish remover.
That's what
This is just like
I want some.
much higher concentrated version of that.
it's
But
like 60 proof.
same stuff.
Would
So,
it still work?
questions on that?
Can
We'll
you
remove
get that
fingernail
without a
polish.
license?
Yeah, really good.
Oh, well.
Yeah, much better than the store-bought kind.
Is it more expensive than the store-bought kind?
I don't know.
And I can tell it was
That's a
because it's the
scam.
same.
I'd have to look at like what
And then
the like. I don't know what percentage the store-bought kind is. Like what? How much?
Yeah, acetone is in
Like, cause this is like 100% acetone.
It's like so small.
I don't know what. Yeah, like the store one is.
try it on my sister.
Yeah, it dries your hand out because it sucks up the water while it's evaporating. So that's why your hand is white. Is because it's just really dry. So, but
No,
but I see it right here.
now I know. If I have a daughter,
Yeah.
no, someone
Just 100%
she accidentally just spills it all over.
Just accident. That would not be good.
My leg is that all dry skin type.
Yeah, you would get cold really fast.
And bath lotion afterwards.
Wait, so if you drink that, it's like hypothetically, would everything just get like?
I'm sure if you drink it, it would not be good.
Yeah, it probably
And your stomach would not be happy.
Would it just take like all of the before it got to you? Yeah.
that's the one.
You'll probably try to crap out of your road. Awful. You have like
Alright, I'll just another. Okay. So it says that nail polish removers are typically, they're actually pretty high. They're about 75% acetone, 25% water. So, yeah.
Oh, wait, never mind, you kinda just answered
You
that.
get pure acetone.
Okay. Any questions on that one? Ready for the next one? Okay. Can you see over here on the camera?
No.
No? Okay. Ugh.
Do you want us to do a
Can you
little
twist
turn
the
around?
stool? Because I have to do it over the sink.
Oh, cool, it's sticking to the ground.
Oh yeah.
Perfect. Oh,
Should I need all these cleaning supplies?
Yeah.
oh, perfect.
Yes?
Wow.
Inhale.
Okay, ready?
Oh, haha.
Okay, everyone ready?
Yeah.
Oh, I see.
I know.
I see it.
I've done this.
Oh, no. Yep.
Explain.
No way.
Is that just water?
Yeah, just water. So in a sense, explain what's keeping the water in the jar.
Is there like something on?
Here, by the way, here's the paper I squirted with water, still wet.
Was there a lid on the jar?
Water is wet.
Or was it just water in the jar and then you just flipped it up to
Well, you tell me, did the water come in and out? Water went in and out, could there have been a lid?
They have to make the jar.
Okay, while you're writing, you've got to pick up the page just a little bit. I'm going to bring another one around for you to look at and explain as well. Okay? So, what I have here is I have a substance on top of water. I'm going to bring it around, and what you're going to do if you want to is just dip your finger in and then pull it
I
out.
think I
Is it gonna make like a?
Okay?
It's gonna like make a thing around
If you don't want to, once you pull it out, just, you can pass the paper towel around to wipe it, or you can just like shake it off.
Dude, shake it off.
but notice how it feels. And if you don't want to, you can just ask someone else how it feels, but I promise it won't hurt you.
How did she has to say it. Yeah, this won't hurt you every single time you do so. It's like, so many things will hurt. And everyone's so scared. They don't.
Someone just, that'd be a good Halloween
I
trick.
thought it was just like on the law.
Make it so like one person starts freaking out, scared.
Walk through a pool.
I had trunk or treat one time.
Trunk or treat.
You know what that is?
I have no idea.
You don't know what trunk or
Oh, wait,
treat
wait, is that like when you decorate them? Oh, trunk. I thought you said truck. Yes.
Somebody had like a cauldron full of like dry ice, and I thought it was a candy thing, like stuff.
You just are like,
Can you tell me?
My mom and like wash my hand off.
It's magical.
Uh-huh.
If you sniff it,
I think
your
it's
nose,
starch.
it'll feel
That's
good.
so weird.
burrito burrito.
Okay, let's talk about the first one. Oh, sorry, give you a second to write down that one.
Wait, were those the same?
No, those are different.
Oh, yeah, I was like,
4
wait.
on the 5.
Yeah, two different things. I just was,
Wait,
Why?
just realized what time it was, so we gotta pick up the pace a little bit.
Usually lighter than water.
Straighten it out.
It probably has something to do with. No, it's probably chlorine.
No, you know how oil works? You know how oil works? Like that.
Yeah, because it's about polarity.
Less dense.
Yeah, it has less to do with density. It has more to do with polarity.
Yeah.
Because water is polar.
I'm just writing that because I already started and like I can't release. Less dense and doesn't mix with
Is that hydrophobic? Is it? It's the same thing with oil.
Okay, any guesses on my jar? How did I make my jar work? Isaac?
So is there just like a little net on the bottom that when you put it on it like sticks, or like it doesn't let any air in or out, so then it's like 6 all together, and then when you turned it, it would let air into it so that it could fall out.
Yes. Let's add, so what's causing them to stick? The hydrogen bonds, right? So obviously it's a trick. If you try this at home, you're gonna make a big mess on your floor. I glued a window screen.
Yeah.
Don't cut up your window screen at home. To my jar. So there are holes on it, so it is, like, water can go in and out. But the hydrogen bonds can grab onto the net, grab onto each other, and it's kind of like the reverse of surface tension, right? It is still the surface tension, just upside down. Now, what I want to do one day is figure out what's the limit of it. Like, how big could I do? Like, could I do a bucket over a student's head? And the water not come out, you know? But at some point, the pressure would overcome the forces a little bit. So, yeah, that's pretty much it. So, thanks for sharing, Isaac. Have a smile face for that. Okay, what about our powder thing? What's going on there, Bryce?
Ooh, so water's polar, and so I thought the other substance was non-polar, because when we talked about the oil and water not mixing, we said it was because water's polar and oil is non-polar, and so then I just did the same thing for this one.
Yep, and it's a very similar concept, right? It's a very different set of forces. Now, once again, to reemphasize, does that mean they're repelling each other?
They just don't attract.
They just don't attract, right? So is it technically correct to call something a water repellent?
No.
It's a water not attract.
I don't know, I mean, yeah, what do we name them instead? But, I mean, that's the whole business of making things, is that it's not repelling the water per se, it's just not attracted to it in any way, right? And that's how this powder is.
So if a question like this came on the AP test and we said it repelled, would that be wrong?
I don't know.
that's a deep question.
Like,
I would like to.
it probably depends on what else you put with the wording. The biggest thing with AP test is they want to see that you understand the forces within. right? So if you used it, but you still talked about the attractive forces of the water to itself, you might be okay. If you simply wrote a statement that just says they repel each other, I doubt you'd give any points for that. So, good question. Landon?
Is that powder starch?
It's not starch, no. Kind of looks like it. It's powder known as lycopodium. We'll use it another day down the road. It does another cool thing, but
the podium.
yeah, so that's,
He does.
it's just a chemical, and that's what it's called. But they actually used to use this. I read somewhere they used to use this as a coating on pills for you to swallow because it wouldn't dissolve until it got to your stomach. Because in your stomach's more than just water, right? So then it would dissolve down there. But okay, let's get in our notes really quick these last few minutes. Just some words to things we've been talking about, like the definitions. Okay, so surface tension, right? That whole idea of how the forces link to each other. Grab on. The biggest thing with all these we want to connect is what it tells us about the IMFs. Okay, so this is the big takeaway with surface tension. The stronger the attraction, the stronger the surface tension. Okay, we want to be able to understand their properties by what's happening at the molecular level. Okay, another one is vapor pressure. Vapor pressure by definition is the pressure that gets exerted by a gas in a closed container. So if you have a closed bottle, some of the liquid can evaporate up here and be in that space up above. The vapor pressure refers to how much has evaporated. So here's the connection. The weaker the forces, the higher the vapor pressure. It's an inverse relationship. So if you see something with a very, very high vapor pressure, you know, oh, that thing does not have very strong intermolecular forces. Yeah.
So this is more like a last time thing. It's like we were talking about like jumping off a cliff into oil. I was wondering, swimming through oil like would be very ineffective because like you couldn't really, it wouldn't do as much.
So I brought that up last period, and that's a very interesting thought too. Yeah, because literally how you swim, if you've ever thought about this, is you're literally grabbing water molecules and you're pushing them, and they go back and you go forward. Well, one of the reasons that helps you grab water so well is because of the hydrogen bonding. That's why if you are a swimmer, you swim with your hand open, because you can actually grab more water because that space in between the hydrogen bondings. It's actually less effective to swim with cupped hands. But with oil, yeah, that's an interesting thought, is oil doesn't have as strong forces, so it seems like it would be really hard, or definitely harder to swim in oil than it would be in water.
Could you even like stay afloat? Like would you
I
just
don't
like
know.
keep moving and just slowly
So
drop?
if we belly flop someone into a pool of oil, we might want to tie a rope around them
Yes.
to get that out
So, you
after.
know,
Yeah, I don't know.
It's like so hard.
That'd be so weird to just be going like this and like
Nothing's happening.
not. Yeah, I mean it's kind of why we can't fly. It's because I can't grab onto the air. There's not enough, you know. I don't know. Like if air was more dense, we could fly. And then we could push the air down and we'd go up.
People could move that.
Okay, boiling point is another one. The connection here we already established, right? But the higher the boiling point equals stronger forces.
What
Right.
is the blank?
Oh, equal. Sorry, that one didn't get filled in. So when the vapor pressure equals the external pressure is when things boil. So the big takeaway, everyone, is what we need, and this is what your homework will have you practice with a lot, is all phase changes, melting, freezing, boiling, backwards and forwards, are all because of intermolecular forces. Whether something does it easily or not easily is all by the ability of, are they pulled together, or is there nothing really pulling them together naturally? So, For your homework, 3.1 is talking the worksheet. Oh, I didn't. It's right here. Pass that up to you real quick. 3.3 is on Canvas. You have 2 AP classroom quizzes and some reading. Oh, sorry.
I always do this. No, I look through my Canvas.
Why did we turn on this,
Would it help Evan? I'll see if I can do it. If I made
Oh.